Yeah, so as Julian just said, this is going to be my PhD work. And I just finished my PhD and turned 30 on the same month. So it's been a pretty busy January for me. Okay. So I wanted to, first of all, thank the organizers very much for the invitation to this workshop. There are people in the room that have written works that I studied very closely during my PhD. So it's really, really cool that I get to present it here. Yes, and as Julian mentioned, my PhD work is overarching theme is boundary layer physics in ocean models. And in this presentation, I will focus on the second project, which is using Bayesian optimization on ocean models. So this, the motivation for working with boundary layer physics is that there is still a lot of work for us to do. And I think this figure from the recent publication Troyer et al. 2023 illustrates this really well. In general, this is the mixed layer depth in OMIP models, the summer mixed layer depth biases. So mixed layer depth itself is not an easy variable to work with, which is really well described in the paper. But from the model biases, we can also see that across the different models which are forced with the same atmosphere, we have radically different biases, and both in low resolution and high resolution, they persist. So this upper ocean turbulence is an unsolved problem that we wanted to address, and I wanted to address in my PhD thesis. So there's different ways that you can attack this problem, and the way that we decided to do it was with automated calibration and with a focus on vertical mixing. And this algorithm that we use for the automated calibration is Bayesian optimization. And this is a method which can be used on a black box optimization problems where the objective function is expensive to evaluate, which is a perfect description of ocean modeling parameterization optimization problem. So the idea is that we have some kind of predefined objective function, and we start with evaluating some random initial points in the parameter space. And then we construct a surrogate model using Gaussian process regression. And the advantage of using Gaussian process regression is that the model provides us with the mean and also the standard deviation over the entire parameter space. Based on this surrogate model, we can construct an acquisition function everywhere in the parameter space. So it's shown here in red. We use the mean of the model minus some multiplier of the uncertainty. In this case, it's 1. And with this, we can use just standard gradient optimization and minimize the acquisition function. We can find basically the points in the parameter space that the optimizer thinks are the optimum points. And then we can evaluate them with the true objective function. And then this process continues. So this optimization loop continues for a set amount of steps. So again, we evaluate points, make a new model, condition the model on the points, and then we construct an acquisition function, minimize it, evaluate those points. The model that we use is our ocean model VEROS, Versatile Ocean Simulator. It's written in pure Python. And as you well know, Python is not very popular language to write ocean models with because it is not really competitive with Fortran in terms of performance, speed, and so on. But Veros has a JAX backend, which makes it competitive with Fortran. And also, when JAX GPU is used, it can outperform it. And I know that earlier today we talked a little bit critically about GPUs, but here we can highlight that not one is better than the other, but having the choice between GPU and CPU can be quite beneficial. So in our experiments, we found that using Lumi GPUs rather than our local CPU cluster consumed 17 times less energy and sped up the simulations 10 times. So that was really beneficial for a project where hundreds of simulations have to be made. Now, finally, we can get to the actual optimization target. So this is the turbulent kinetic energy scheme from Gaspar et al. Sorry for the math. I tried to make it colorful. And the main things here to notice is that the vertical turbulent fluxes are scaled by the diffusivity and viscosity, which are in turn scaled by the parameter Ck. Then we have the TKE dissipation, which is scaled by C epsilon. We have vertical diffusive flux of TKE, which is scaled by alpha TKE. And then we can also set a minimum diffusivity and viscosity in the ocean interior to mimic the breaking of unresolved internal waves, kind of like in KBP. And so that gives us a 4 free parameter space to optimize. And the default values and ranges are given here on the slide. An important part or feature of this parameterization is that the critical Richardson number of the model is proportional to CK and C epsilon ratio. So we have 2 optimization experiments in this first project that was a part of my thesis. They have 2 different goals, but the targets are similar. So we want to compute the error between mixed layer depth fields simulated by using the parameterization picked by Veropt and some target mixed layer depth field. In the twin experiment, we wanted to assess the sensitivity of mixed layer depth to TK parameters. We used a full parameter space. And here, and we also wanted to test the robustness of the model, of the optimizer. We used very coarse 4x4 Veros setup for this because we wanted to evaluate 180 points. That was before we had access to the Lumi supercomputer. And the OBS optimization experiment is quite a bit smaller. So here the goal is to minimize Veros mixed layer depth bias. We reduce the parameter space to only 2 parameters based on our twin results. We use 1 degree model here, and because of this, we only had 40 evaluated points. So the twin results were quite encouraging to us. Here you can see the mixed layer depth zonal average. The default is shown in black dotted line, and then the color is all the experiments. The progression of the mixed layer depth error can be seen here, and this is the initial randomly selected points, and this is points selected by Veropt, and there's luckily a large difference here in accuracy. And the best that we could get was 1.18%. So that was very, very nice. We also found that the critical Richardson number basically sets the mixed layer depth in the model. This is similar to second moment closure models as well. So that was a nice confirmation, and we were able to recover this critical Richardson number to 2.1% accuracy. So since this number is a ratio between 2 parameters in the model, we had a higher deviation of those parameters, but that is not surprisingly. And in the end, we don't want to have perfect parameters or one set of parameters, but we want to recover the mixed layer depth field, which is closest to observations, and sort of the entire parameter space that can reproduce that. So encouraged by those results, we went on to the OBS experiment. And of course, things get more complicated when you work with observations as target. So we found a pretty similar situation as in the 4-degree case. We have a large space in the parameter space where the bias is minimized. And the default parameterization actually falls within this space, but the bias is still significant. And we found this is because, again, just as in the case of the twin experiment, we can kind of deepen and shallow when I don't think that's a word, the mixed layer depth in the entire ocean. So we can improve. So here in thick black line, that's mixed layer depth climatology. So we can improve the situation in one point of the ocean, but that comes at a cost of another biases. So we wanted to see whether we can do better. And because of that, we wanted to extend the experiment. So this is the results, quite preliminary results of this full 9-dimensional experiment that we did very recently over December and January. So we still stick with the Veros 1-degree setup, but this time we have 463 evaluated points because we gained the access to the Lumi supercomputer. So we could run a lot more simulations in parallel, 32 to be precise. And here we still have the goal of minimizing Veros mixed layer depth bias, but we also added some targets to have more control over other aspects of the model. So the extended parameter space includes the whole TKE parameterization. We also added the mesoscale eddy closure, and this is by Eden and Greatbatch, so not the classical GM. Here we have EKECK and EKEC epsilon. CK scales the GM parameter in the parameterization, and EKEC epsilon scales the EKE dissipation. And in this parameterization, the KGM is set using the EKE budget in the model. We also wanted to investigate the impact of forcing fields on the mixed layer depth and other aspects of the model. So we multiplied our mask of tau x and tau y, so wind stress zonal and meridional, and the salinity mask by just parameters. And in terms of targets, so we have mixed layer depth error just like before, but we extended our the field that we looked at. So before we had 50 south to 50 north, and then we wanted to cover more of the Southern Ocean, so we extended to 60 south. We added ACC and AMOC errors relative to the observed values noted here on the slide. And we also wanted to have more control over what happens in the deeper upper ocean in the tropics, because there the mixed layer is quite thin. So we added the 18 Celsius isotherm depth error as well. So the total error is basically just a sum of these previously mentioned errors, and there's a smarter way of doing this, and we're working on that. But this was kind of the preliminary way of doing it. So we weighted the 18C error by 3 because it turns out to be tiny compared to the others. And we also add the boundary punishment. So Bayesian optimization has this problem of picking boundary values in the parameter space. So we wanted to counter that. That backfired a little bit. But we can look at the results of the optimization. So here are all of the runs, and the histograms of the errors named before, and boundary punishment and total error. So we don't get the perfect model, but we see that almost all of the runs show an improvement in mixed layer depth, and also in ACC, which is really cool to see. This comes at apparently at a cost of sort of the representation of an internal temperature in the upper ocean, in the tropics. So that's something that I want to definitely look into closer. We can also look at what typical values of parameters the optimizer chooses. So in Bayesian optimization, basically, as a rule of thumb, if the optimizer picks uniformly in a parameter, that means that it's not so important for the objective function. But if there is some decisive peaks, that means that it is very confident that this is the part of the parameter space that brings us closer to the optimum. So it was kind of surprising to see that even though previously we could not improve the mixed layer depth bias, CK seems to still be the most important parameter for the vertical mixing. We also, I noticed that there is some double peaks in some of the parameters, and I think this is because the boundary punishment might have been too harsh. So there is something definitely to improve here. And as we discussed yesterday, just looking at one result is really not enough, and I'm gonna have a lot of fun looking at the ensemble in the next months. But I wanted to show you the example of an optimal solution to kind of look at have a closer look at the patterns that emerge. So first of all, it's really cool that this really large mixed layer depth bias that we see in the default Veros gets actually reduced, and this doesn't. So one spot doesn't come at a cost to the other. So we can kind of see improvement all over the global ocean, which I thought was much better than I expected. And you can see that also in the two-dimensional map of the mixed layer depth. So here we have the default parameters, the relative mixed layer depth difference compared to the climatology, and here we have best parameters. So we can see that both the Southern Ocean, high latitudes, they show significant improvement, but also the tropics show less biases. And we can do this with keeping the ACC and AMOC realistic. And as I mentioned before, in this case, in this simulation, this is also true that we get a little bit larger 18C bias. This could be due to how I defined this error, but I'm going to look more into this. There is some interesting things that I wanted to discuss about the parameters from this run. For example, alpha DKE. In the original Gaspar 1990 paper, where they tuned the DKE scheme in just the column model, they pick originally alpha DKE to be 1, and this is kind of a standard thing to do. But this very large number of 30 is an artifact of when then the model was adapted into a 3-dimensional model, and we had very coarse resolution at the bottom of the ocean, and then TKE would start to spike. So they really increase the diffusivity. But with our 60 vertical layers, we see that the model tends to the original Gaspar value, which I think was really interesting and cool. We also see that in this particular run, we see zonal winds being forced to be weaker and meridional to be stronger. And this is actually consistent with ERA 5 and ERA interim biases compared to satellite observations that were shown by Rivas and Stoffelen. So here we have the satellite observations, and we see that zonal winds are overestimated in ERA 5 and ERA interim, and meridional winds are underestimated. So that's also something that looks physical and not an artifact of the model. And another interesting thing was that the EKCK and EKC epsilon, so the mesoscale eddy closure parameters are much different than the default. And I really thought up until yesterday that this was just because we have a simple model and we have to push this parameterization to get something realistic in the Southern Ocean. But the interesting discussions yesterday actually showed that there might be some physics there, because I've seen other people discussing how they had to reduce the KGM to get a more realistic representation of stratification in the Southern Ocean. So I think that's really exciting. And this is not just a one-off. So if we look at just the entire parameter space, the EKC epsilon, so the parameter which diffuses, dissipates the eddy kinetic energy, it doesn't matter so much, but the model really, or the optimizer really pushes for low values of the CK parameter, which scales the GM coefficient in the parameterization. So I find that really exciting as well. Looking forward to look into that, and also look more into the research that I've seen here. And so you can see how this EKE-CK parameter actually affects the KGM parameter in the model. So this is the zonal average from default, where KGM is generally an order of magnitude larger than in our best parameterization. So in conclusion, surprisingly, Bayesian optimization actually works. We can reduce mixed layer depth biases in the model and keep realistic ACC and AMOC. And when you think about the layers of abstraction, that you have to collapse your error into just one number, and this optimizer has to kind of interpolate between the known points in the parameter space. It's kind of shocking that it works. And we found also that the mesoscale eddy closure and wind field biases have a large impact on mixed layer depth biases in our model. But we cannot start, or we can celebrate for a little bit and then get back to work, because of course there is this big overarching problem with tuning, which is does your model get better for the right reasons? I think this is a very fascinating question, and I've seen a lot of people kind of take it upon themselves in the community. So I think this will take some time, but I'm ready to get sucked into this black hole. But just in terms of technical future work, we want to take upon us coupled system calibration, and this is also kind of a can of worms. But it would be interesting to see what we can get when we don't have biases coming from lack of ARC interactions. This is, of course, a longer discussion. This could go really wrong, but I would like to try it. And of course, a very fundamental thing is the mixed layer depth is a highly nonlinear variable. So what we do is tune the annual average, which it should make us a little bit nervous. And I think the ideal case would be to tune summer and winter mixed layer. Our issue is space, of course. So when you have hundreds of simulations, you have limited space to store them. So we currently store 10-year averages, and that's how we kind of save it. So it's kind of difficult to get seasonal mixed layer from that. And we're also working on Verob 2.0. So updating the package, making the structure better, and we also want to make it applicable to more models than just Veros. So this is coming, I think, this summer, hopefully. And thank you for your attention. I'm happy to take questions, discussion. And before I start answering questions, I just wanted to say two things. One, you can contact me on email if you want to discuss optimization. I think it's super fun topic to talk about. Or if you want to optimize your model, call me. And I also wanted to advertise our survey for our discussion tomorrow. So it's not too late to answer the survey. And if you thought about some stuff during this talk or tonight, please fill it out, and we're gonna have a fun talk about it tomorrow.
Thank you. Thank you very much, Marta, and thanks for raising again this question of the survey. We've probably had that 10 or 11 answers so far, so if you want to share your thoughts there, that would be very helpful for helping us steering up the discussion tomorrow. But before that, we're here for question and answers for Marta. I'm sure there will be plenty. I think you were probably first, but I'm not quite so sure.
Thanks, Marta. It's very interesting. I always like seeing applications of this Bayesian optimization, because we've played with that a little bit in Southampton. Well, Adam more particularly than me. Okay, sorry. But as a physicist in oceanography, I'm more interested in what these parameters do to the model. So for instance, you've changed the vertical mixing in the model, and you found that the overturning and the ACC transport are improved. Can you say anything about what that range of the parameter space does to the overall mixing? So for instance, in the work I've been doing recently, I've found that if you reduce the mixing in the Southern Ocean, you strengthen the ACC, but if you increase the mixing at lower latitudes, you increase the AMOC strength. So it would be interesting to talk to you about that.
So this is something that the ACC and AMOC error is something that we just added. So up until very recently, I was just looking at the upper ocean. I know from Niels Brüggemann that when they were playing with Icon, it actually, for AMOC, apparently, when you reduce the kappa min, so if you reduce the minimum diffusivity in the ocean interior, that really affects the circulation, and other parameters kind of affect the upper ocean more. But I definitely want to dive deeply into the question that you bring up. I actually am quite surprised that most of an overwhelming majority of our simulations with such different varied parameterizations result in unbiased AMOC and ACC, and I think that is maybe suspicious. So I'll look into that. Thank you.
Dave. Hi, thanks for a nice talk. I was just wondering about the relationship between, so you've been optimizing quite low resolution models here, and just wondering about the relationship with kind of higher resolution models, and I'm wondering to what extent you could optimize things in a low res model, and to what extent that would carry over. So if you put the same parameter set, you start you did the test of the two parameter sets in the high res model, would you get better results, do you think?
Yeah,
without optimizing, because obviously I guess optimizing the high res model would be an expensive thing to do.
Yeah, this is a really interesting question. I think that you did this in history matching, right? I studied this paper very intently. So for example, I think this critical Richardson number, which I found this is quite embedded in the theory behind this parameterization, I think that would definitely carry over. So, picking your critical Richardson number, obviously if you get it higher, then you're gonna have more mixing. So I think, and I find it is very useful to sort of like take these optimization results and then go back into sort of looking at what these parameters mean in theory. I think that's where you get like the most useful results that you actually can carry over to other models. Yeah.
Thanks.
Thank you. It's a very nice talk. Could you say a little bit more about that boundary punishment and what you think is going on there? Because
yes.
that looks very interesting.
Okay, so this is something that is very well known in Bayesian optimization literature, and I can actually. So you see, even in this kind of very simple problem, we have a tendency of the optimizer to pick boundary values, and this. I do not understand this completely, but this has to do with kind of the volume. The volume of the parameter space is higher at the boundary than inside, and then especially when you have parameters which vary very slowly or very little, then you're gonna have your optimizer tending to pick boundary values. So what we did was very simple. We basically made an exponential curve. So you add punishment. So you lower the objective. No, you make the objective function value higher. For if the optimizer picks the parameters that are at boundaries. And the reason why I say it's backfired is because we see these double peaks, and you can see it much better in the C tau x and C tau y parameter space. So it looks like this boundary punishment maybe was too heavy because it really impacted this, for example, these results. There is a smarter way of dealing with it. There is a special acquisition function that that is supposed to counteract this bias really effectively, called BOC. But we have it implemented, but I haven't really looked into it. But yeah, thank you.
Thank you.
If just right before, if I may just jump in on this question, so I'm not aware of similar like boundary problems in formulations of Bayesian optimization that don't like use emulators. Like if you were simply able like to formulate this as a variational problem and fully evaluate your gradient, I'm not aware of any like similar boundary problems. So is that really due to the specificity of using GP emulators?
Yeah, I think so. Yeah, and I think also the form of acquisition function. So you can do a Monte Carlo acquisition function as well, which maybe doesn't have that issue. So I think it's specifically the formulation of the acquisition function that is the reason for this. But yeah, I've only encountered this issue with Bayesian optimization.
Thanks.
Thanks for the very interesting talk. So I have a very stupid question. Could you explain why it's called Bayesian optimization and what it has to do with Bayes' theorem?
Yes. So it actually comes from the Gaussian processes where this emulator is based on, and this is really because God, I could use a whiteboard. No, okay. So the way that Gaussian process regression works is that you can make this surrogate. You achieve this model by basically using the Bayes formula on a Gaussian. Maybe I can. Okay, sorry. I want to illustrate this because this is an interesting question. Do I have? It was not a stupid question, by the way. Okay, I'm bringing up my PhD thesis here, and we have the Zoom, and I share my screen. Yeah. So here it is. So the way that we can even arrive at the formulation of the Gaussian process regression that is useful for us is by using this Bayes rule. And this leads us to having a formulation of, this is very opaque. Sorry about that. essentially we can describe the Gaussian process by only mean and covariance, and it starts with Bayesian Bayes rule, and what you end up with is basically a model purely described by mean and and a kernel, and this is really useful because you can apply it in constructing these models really easily in this computing problems. So I'm not a mathematician. I bet a mathematician could you explain it better.
I think we do have a question online by Arne. Just before, I guess the whole point there is that for those familiar with Bayesian formulation to parameter tuning. So the question is to estimate the posterior distribution based on a prior and some observations, and the key aspect there is the fact that you don't know the likelihood, and what you're using here is really much GP to approximate the likelihood and find a way that's amenable and tractable, and in particular that can be minimized through gradient-based optimization. So that's the whole point here.
That is really
as far as I understand it.
That is a really good way of putting it. Thank you very much.
No worries. Arne.
Yeah, thanks, Marta. Great talk and big potential, I think. Now, as far as I can see it, you optimized basically the mean distribution of mixed layer depths.
Yes.
Now, the mixed layer module is also used to represent, let's say, the deep water formation and the sinking, which in return, in the end, is also connected to the AMOC. Did you look at the let's say the maximum mixed layer depths in winter and to see if this is also reasonable after your optimization?
No, but this is definitely something that we will do. Is a great point, and yeah, we will have to. So question of space. I think we will have to rerun some of the best parameters in this seasonal resolving, temporally seasonal resolving. Setup and look at the seasonal signal, because I think that might be very significant.
I'm asking in particular, since you could easily, for example, overestimate, let's say, the mixed layer depths in winter, and having a deep water formation down to the bottom, for example, which would create a very strong AMOC, so you would get the right results, but for the wrong reasons.
Yes,
that's the motivation of my question.
Yeah, and I totally agree with you, and this is something that we will definitely check. Thank you very much.
Thank you.
Good point.
I think Mike Bell has a question now.
Thank you, Martha, for your talk. Obviously, you're trying to spare us some of the technical details, because but I'm just wondering whether you could perhaps describe a little bit more about how your system works. I mean, are you running a whole sequence of 3D model simulations and then compare with different parameter settings and then evaluating the differences from the observed mixed layer depths? Is that the sort of, and then you use and then you use those results to do a best fit type thing?
Exactly. So what we do is really what is shown here, except we have, of course, a 9-dimensional parameter space. So in the beginning, we literally just pick random points. And then the way that these points are evaluated is by running the simulation. So we have a algorithm that takes points from Veropt and inputs them into the model. And then the model runs in parallel. So we were not able to run so many parallel runs at the beginning, but with Lumi, we were able to do 32 at a time, which was really nice, because it of course takes a long time to run these simulations. And then once the simulations are done, and if they have succeeded, then some objective function is calculated from the results. And that is also done automatically by an algorithm. And then these objective function values are then fed into Veropt again. And then this surrogate model construction, acquisition function construction, and minimization, that happens inside Veropt. and then Veropt sends this information again to the model, and that happens for a set amount of runs. And in the case of Lumi simulations, we had one initial round, which is kind of low, I would say, and then 20 Bayes, so 20 optimization rounds. And we only completed 14 because we ran out of computational time. And then we had 32 parallel runs.
Thanks a lot for those numbers. Next question by Akash Sani.
Thanks for the great talk. I was wondering if there is any danger of getting a different set of parameters but minimizing the same loss, as in getting the same performance of the mixed layer depth, but now you have a different set of or different value of that vector, CK, etc., etc.
Is that dangerous, you're asking? Or
no, as in is there any limitation, as in you ran this program again and there was some, maybe used a different random seed or something, and you got a different value of those optimal parameters for the same mixed layer depth? Can that happen?
For the same mixed layer depth and different parameters? Yes. We actually find that there is large spaces, large regions of the parameter space which simulate similar results. I don't think that's necessarily dangerous. Okay. You also can find this in history matching, that there is large regions of the parameter space which simulate acceptable results. I guess the risk is in not considering an important aspect of the model. So you might get good results in mixed layer depth, ACC and AMOC, but you overlook something else that is completely crazy. Yeah.
Right, thanks.
Remy has a question.
Yes, thank you for some nice talk. I was wondering about you didn't mention lateral mixing processes, unless I missed it or unless they are hidden in your TKA.
No.
You didn't optimize lateral processes at all?
No. So we limited. We are limited amount of people that are doing this, so it's mostly me that is taking care of it, and so I'm kind of taking different parts of the model once at a time. So I am, I'm now really experienced with the vertical mixing and a little bit experienced with these other parameterizations, but it also takes time and expertise to figure out what are the good ranges for the parameters, what is the meaning, what parameters should be optimized. So I'm so happy to take comments and notes on what you think I should work on next.
So the other question is, what is a special? I didn't get whether you get a spatially varying optimized coefficient, or whether you get a single value for the whole, because you optimize TKE parameters, right? Does that result in a spatially varying vertical mixing coefficient, for instance?
No. So we said, maybe I don't understand your question, but we set the parameters, and those are the parameters that the model runs with. So we don't vary them or stochastically or anything like that.
Okay. So the spatial variation are predicted by the TKE equation.
Yes.
So you fit only the parameters of the TKE. All right. Thank you.
Thank you.
I do have a comment or question, and since James Hall is here in the room, I was wondering whether any of you is aware of people having used things like CFC data for calibration exercises. I mean, we saw this afternoon in Marion's presentation that indeed CFC was interesting for assessing model solutions when it comes to vertical mixing parameterizations, and it seems that could be like a very helpful additional constraint for those models. What do you think of that, Marta? James? Marta?
Oh, no, we talked about this right before, and I'm not familiar, but I'm happy to talk about it afterwards.
Well, I think CFC is
Yeah. CFCs are an interesting tracer. They're underexploited. There's a tremendous amount of data, millions of measurements, very precise measurements, and inert tracer in the ocean. So it's great. It's often thought that it's maybe a biogeochemical tracer, but it's purely physical, as Mario pointed out. And the boundary condition is really well known. There's a surface boundary condition. There's nothing else. Once it gets in the ocean, it's inert. And we have all these measurements throughout the ocean on repeat sections. And so I think it's useful in the standard way of doing simulations and comparing to data, but actually in the Bayesian approach where you could imagine using it, could be an interesting constraint. There's a lot of data. So
probably an easy catch for you, Martha, to focus on, right?
Yeah, that
Cool.
sounds good.
So food for thoughts for the coffee break.
Thank you.
Are we getting to the coffee break?
Yes, please.
Other questions in
Sorry.
the audience?
No,
Okay,
no
so with this, we'd like to thank again Martha for the great talk and
Thank
really
you.
nice discussion.